Today we're going to be talking about standing waves, and we're going to work through a problem. So consider a wave on an 80 centimeter string with a fundamental frequency of 100 hertz. So this tells us our L is equal to 80 centimeters. Remember that decimal point there tells us that both of these are significant figures. And let's just put this in meters, 0.80 meters. And then a fundamental frequency of 100 hertz. That tells us F1, the first harmonic, which is fundamental frequency, is 100 hertz. All right, so in part one, we're asked to draw the fourth harmonic, label all nodes and antinodes, and then calculate wavelength and the frequency of the fourth harmonic. So a good thing to remember is that for the fourth harmonic, N is 4. N is pretty much just the number of the harmonic, and it tells us number of antinodes. All right, so if we draw this, here's our string. We're going to break this up into 4 antinodes. Remember, our antinodes are regions with maximal vibration. These are the antinodes. And then our nodes are regions with 0 vibration. That's where we had destructive interference of our waves. Nodes. And the number of nodes is always equal to n plus 1. So the number of antinodes plus 1, which is equal to 5 here. All right, so what is our wavelength? You remember, wavelength, one wavelength looks like that. We measure it from the start to the end of just one wave pattern. So we can count how many wavelengths we have along the string. There's 1, and there's 2. So we have 2 wavelengths along our length, which is L. So if we solve for wavelength, that's 0.80 meters over 2. So lambda is equal to 0.40 meters. And now we need to find the frequency of the fourth harmonic. So the frequency of any harmonic is equal to n times F1. So for the fourth harmonic, n equals 4. So we have F4 is equal to 4 times F1. We have F1 up here, so now we just plug that in, and we get 400 hertz for our fourth harmonic. Now in part B, we're asked to repeat this for the seventh harmonic. So N, we know right away, that's 7, and we can draw this. And we need to break it up into 7 antinodes. I find it helpful to mark out where each node is going to be before starting to draw. And we can see we've got 7 antinodes. And we can tell we're going to have 8 nodes, and they're going to be here. All right, so we want to find the wavelength for the 7th harmonic and the frequency for the 7th harmonic. So wavelength, we can count out how many wavelengths we have again. So there's 1. Notice each of these wavelengths is going to be shorter than the wavelengths for the fourth harmonic because we need to fit more antinodes in and more wavelengths into the same length of string. That's 1, 2, 3 and a half. So we have 3.5 wavelengths in L, and you can see for every 2 nodes we get 1 wavelength. So if you wanted a little shortcut, you can just go 1, 2, 3.5. 3.5 is 7 halves. lambda. So now we can solve for lambda. We're just going to divide both sides by 7 halves. We're just going to multiply this side by 2/7. So it's going to be 2/7 times 0.80 meters. And that turns out to be 0.23 meters. Next, we need to find the frequency. So we can come back over here. We have n equals 7. So F7 is equal to 7 times F1. 7 times 100 hertz is 700 hertz. So in this problem, we drew 2 different harmonics for this string, and given the string length and the fundamental frequency, we were able to find the wavelength and frequencies for those harmonics.